So now talking about more important points regarding this is, if you see, leaving group is leaving in the first step, which is the rate determining step. So for this reaction to proceed faster, better the leaving group, better is the rate of the reaction. Better the leaving group, better is the rate of the reaction. As it happens during the rate determining step. I am writing rate determining step as RDS. I have told you that you can use RDS for the rate determining step. So if I talk about the reactivity with the alkyl halides, then obviously Ri is going to be the most reactive. Why? Then RBr, then RCl, and then obviously RF. This is the rate or reactivity. Can you tell me why? Because we know that I minus is the best leaving group. Why I minus is the best leaving group? Because it is the poorest base. HI is the strongest acid, so conjugate base, that is I minus, is going to be a poor base, isn't it so? So that is the reason with it. Alright, so that is the reactivity order when I talk about the leaving group. If I move further, I am forming a carbocation. So obviously the stability of carbocation plays an important role. Alright, I can also say reactivity also depends on stability of the carbocation formed. Stability of the carbocation formed. Now how does it depend on the stability of the carbocation formed? Obviously tertiary carbocation, then secondary, then primary, and then obviously methyl. Alright, because tertiary carbocation is the most stable, we are forming the carbocation over here. Now we know that whenever carbocation is formed, rearrangement is possible. As carbocation is formed, rearrangement is possible. Is that clear? Please remember that point. Wherever you have carbocation which is being formed, then rearrangement will be quite possible. Now let's talk about the solvent factor. If I talk about the solvent factor, that how will a solvent have an effect on SN1 reaction. Now see, your reactant is neutral. Reactant is what? Neutral. What is the intermediate which is being formed? Intermediate formed is carbocation which is charged. Intermediate formed is carbocation which is charged. Now let's say I have two possibilities. One is a polar solvent and one is a non-polar solvent. Alright, if I look at the two possibilities, one is a polar solvent and the other one is a non-polar solvent. Now if I look at non-polar solvent, polar solvent will have no effect on what? Reactant. And if I look at non-polar, non-polar will also have no effect. But if I look at the intermediate, that is the carbocation, it will stabilize it. The polar solvent and especially polar protic solvent, polar protic as well as polar aprotic solvent is going to stabilize the carbocation. It will again have no effect. Your transition state is also initially formed. See, there is a transition state which is initially formed. As this bond starts getting weaker, that will be called as the transition state. Now if I talk about the transition state, that is going to be a little charged. transition state, I can say that is little charged. So obviously polar solvent again will slightly stabilize it. Again no effect. Is that part clear? So as you can see, the intermediate which we are forming, the carbocation, can be stabilized by a polar solvent. So obviously when it is stabilized by a polar solvent, the reactivity is going to increase. If I take a non-polar solvent, then there is no stabilization. And we know more the stabilization, more energy is released, easier the work is. So I can say SN1 reaction will be highly favored. I can simply give a statement that SN1 reactions will be highly favored in what type of solvent? SN1 reactions are highly favored in polar solvents. SN1 reactions are highly favored in polar solvents. I hope this point is absolutely clear to you. Alright, please don't forget this. That is one point. And the other important point is strength of the nucleophile. Strength of nucleophile is not important. Strength of the nucleophile is not important. I hope that part is also absolutely. These are very two important points regarding SN1 reaction. Okay. Now let me talk about the statement regarding the racemization. That 100% racemization is there. See, the problem is certain studies have shown. In some books you will find that it is written that it's 100% racemization. No. Actually, studies have shown that there is 100% racemization is not possible. See, why 100% racemization is not possible? First, I'll write the statement. That statement is that nearly 100%, see, not 100%, nearly 100% racemization takes place with some amount of inversion also taking place. That is another important case. Now see, what let's say you will definitely have, in the first step you are going to form the carbocation and you are going to form the leaving group. Now tell me one thing, has leaving group left, like it's like gone forever? No, right? Leaving group will be there in the reaction vessel or not? Tell me. That is chemistry. It is not someone is leaving you. You're not ending some kind of a relationship. That person is gone. And even if the person is gone, it's not like the person has passed away. Similarly, leaving group has not passed away. Leaving group is going to be there. It is going to be there, right? So, tell me, there will be certain kind of little amount of interaction which will be there or not? But it is going to be there because it is a positively charged and it is a negatively charged species. It is definitely going to be there. Certain amount of interaction will be there. And when this certain amount of interaction is there, the attack of the nucleophile will first initially take place from the back. You understand my point? There will be certain amount of interaction between the carbocation and the leaving group, and because of that, the attack initially has to take place from the back side, and as it takes place from the back side, some amount of inverted product will also be obtained in a larger quantity, obviously. So 100% racemization, we cannot guarantee 100%. We can say, yeah, nearly 100% racemization is possible. So what reason I can say, as carbocation and leaving group are charged species they will have certain interaction which will lead to backside attack by nucleophile, hence inverted product is also obtained. Hence inverted product is also obtained. I hope this part is clear to you, right? So this is nothing but summarizing the SN1 reaction. You can see SN1 reaction is a two-step reaction where the first step, that is the formation of carbocation or leaving group goes, is the one which is going to be the slow step, and that is going to be the rate determining step. Then the next step is attack of the nucleophile. Now as carbocation is a planar structure, the attack is possible from both front and back side. When both is possible, you can have both D and L isomer if optical activity is there. Hence, that means you will have racemization, but we have talked about the fact that 100% racemization is not going to be there. There will be some amount of inverted product which will be in greater quantity. Alright. Now, the rate kinetic says that the rate of the reaction is only directly proportional to the concentration of the substrate. It has got nothing to do with the concentration of the nucleophile. So by increasing the concentration of the nucleophile or by even increasing or decreasing the strength of the nucleophile is not going to have any effect on the rate of the reaction. Why? The strength of the nucleophile is also not going to play a factor because we have already formed our carbocation and that is not the rate determining step either. Is that part clear to you? Then we talked about the reactivity. Better the leaving group, better is the reaction. Why? Because leaving group is the rate determining step again. Similarly, formation of carbocation is taking place, so stability of carbocation will also play a factor. More stable the carbocation, more will be the rate of the reaction. Then we talked about, we know that carbocation is formed, rearrangement is quite possible. Similarly, next part, solvent factor. We have two types of solvents, polar and non-polar. Basically, we can have polar protic and polar aprotic solvent also. Now, polar solvents are going to stabilize the carbocation. As they stabilize the carbocation, they bring down the activation energy. When they bring down the activation energy, obviously, SN1 reactions will be highly favored in the polar solvents. SN1 reactions are going to be highly favored in the polar solvents. So this is about SN1 reaction. We are going to take up certain examples to understand SN1 reaction. Alright, let us look at the examples of SN1 reaction. Now, the most common example is acid catalyzed substitution of alcohols. Now, why acid catalyzed? We have discussed this part during the elimination reaction. Now, we know that OH minus is not a good leaving group because it is relatively a good base. We know that water is a poor base, so it is a better leaving group. So what we do? We protonate the alcohol. Similarly, what we did during the elimination reaction. We protonate the alcohol, and by protonating the alcohol, we are able to form water which can result into a good leaving group. So during acid catalyzed substitution of alcohols, you usually take an alcohol. I'll take two examples to explain this thing. The first one is, let's take butanol. Now when in butanol you catalyzed it, alright, now what are you going to form? You're going to form this. Now when you have formed this, obviously you have done a crime, you have given oxygen a positive charge. Oxygen will not take the positive charge and what will happen? The water is going to leave. When water leaves, you will form your carbocation, formation of carbocation. Now when you have formed the carbocation, then a nucleophile can attack. I'm just showing nucleophile as nucleophile. Nucleophile will attack and you're going to get this new. Now there is a certain thing. This is going to be one product, and when nucleophile attacks, before that there can be 1,2 hydride shift. Why there will be 1,2 hydride shift? Because the secondary carbocation which will be formed, this is a primary carbocation. What will happen? You will form this, and then nucleophile attacks on this. Now the feasibility of this type of reaction is very low. This SN2 pathway cannot be explained for this. I can write it, feasibility of this reaction is low as primary carbocation is formed. As primary carbocation is formed. So explaining it on the basis of SN1 is actually wrong. But that is one part. How can we explain for what kind of reaction? Let's say you have this molecule now. Neopentyl alcohol. You have neopentyl alcohol, and when you acid catalyze it, when you do acid catalyzed reaction, you are adding the acid, you are going to protonate the alcohol, and this is what you are going to form. Now when you have formed this protonated alcohol, oxygen will take back its electron and leave as water. Now when oxygen leaves as water, you are going to be left with the carbocation, which is this primary carbocation. Now this primary carbocation can undergo rearrangement by 1,2 methyl shift. When this 1,2 methyl shift takes place, what will you get? You will get a tertiary carbocation. This is the tertiary carbocation which you will get. And now a nucleophile can attack at this, and this is the rearranged product which you are going to form. So this is nothing but SN1 pathway. Now see, one thing you have realized, as stability of carbocation is an important factor, then obviously tertiary alkyl halides and tertiary alcohols are obviously going to follow the SN1 pathway. Alright. Primary alkyl halides and primary alcohols are not going to follow the SN1 pathway unless and until they are resonance stabilized. Why? Because formation of primary carbocation as such, if it is not rearranging itself, it is very difficult, which we have seen during the elimination reactions. So what do they give? They give SN2 pathway. So next, let's talk about the SN2 reaction, which will be our next heading. That is going to be bimolecular nucleophilic substitution reaction. Now what happens during this reaction? You can relate this with E2 reaction. If you remember E2 elimination, it was a single step reaction. So this is also a single step reaction. What is this? It is a single step reaction. It proceeds via formation of a planar transition state. Via formation of planar transition state. How does that happen? Let's say this is your carbon and there is a leaving group which I am showing like this. Obviously it is sp3 hybridized carbon. There is a nucleophile in the vicinity. It will come and attack. So what happens here is the formation of the bond starts taking place. The formation of the bond between carbon and the nucleophile starts taking place, and at the same time the carbon and leaving group, the bond shared between the carbon and the leaving group starts getting weaker. At the same time, both of them are happening at the same time. So what happens? It forms a planar kind of a transition state which looks like something like this. Alright, there will be delta negative charge on the nucleophile, there will be delta negative charge on the leaving group, as well as there will be a delta positive charge on the carbon. This is nothing but, you can say it is sp2 hybridized. Alright, what has happened at the same time, as this bond starts getting stronger, bond is getting stronger, at the same time this bond is getting weaker. At the same time, this bond is getting weaker. Eventually what will happen? Eventually this will break and leaving group leaves. Now, another important point, nucleophile can attack only from the back side. Why it can attack from the back side? Quite obvious, when the front side is occupied, how can it attack from the front side? Front side is occupied by the leaving group, so obviously it cannot attack from the front side. So where it can attack from? Back side. Hence this leads to inversion of configuration. Hence this leads to inversion of configuration. I hope that point is clear to you. The attack has to take from backside. Alright? Attack takes from backside. One thing which we are very much clear about is that there is no formation of carbocation hence rearrangement does not take place. Hence rearrangement does not take place. I hope that point is very much clear. SN1 will give rearrangement, SN2 is not going to give rearrangement. Now, when the attack and leaving group are going at the same time, I can say the rate order or the rate kinetics is rate is equal to concentration of substrate as well as concentration of the nucleophile. So now the strength of the nucleophile and the concentration of the nucleophile plays an important role. So on increasing the concentration of nucleophile, and strength of the nucleophile, rate of SN2 reaction increases. Now, you have understood this part, that concentration is obviously going to play an important role as it is coming in the rate law. Now, one more thing which plays an important role is the steric hindrance. If there will be too much of steric hindrance over here, if there is too much of steric hindrance, then attack will become difficult. How can this nucleophile approach? If this thing becomes bulky in nature, how can the nucleophile approach? So steric hindrance plays an important role. Steric hindrance plays an important role and decreases the rate of the reaction. Alright, it is going to decrease the rate of the reaction. That means reactivity order is going to be primary, then secondary, and then tertiary for carbocations, or you can say alkyl halide and alcohols. That is going to be the reactivity order for SN2 reaction. Similarly, reactivity order for leaving group, as leaving group is again involved, there is only one step. So as leaving group is involved over there, better the leaving group, better is the reactivity. So I can say better the leaving group, better is the rate of reaction. So basically this is going to be the order of the reaction. Why is this the order of reaction? Again the same thing, I minus is a better leaving group, then Br minus, then Cl minus and F minus. So this is nothing but bimolecular nucleophilic substitution reaction or SN2 reaction. Just remember a thumb rule that primary alkyl halide and primary alcohols are going to prefer SN2 reaction. They will not give SN1 reaction. Whereas tertiary alkyl halide and tertiary alcohols are going to give SN1 reaction because the stability of carbocation is very much high. SN2 reaction and SN1 reaction can be given by both. Both can be given by basically secondary alkyl halides and secondary alcohols. How to decide what will be given, when it will be given, we'll talk about that. So we have seen both SN1 and SN2 reactions. We are going to do a comparative study between SN1 and SN2 reaction to understand it better.